Alright guys, we're going to go over the study guide that was assigned on Thursday for you guys to complete. And don't forget, after watching this video, the same study guide answer solution sheet will be also posted. Please keep these together. You should have yourself your physics folder on your drive and keep these together and organized, because when we have a test or a quiz in the future, you may use these study guides for it. So please don't lose them. Alright, so starting off with a few review questions. The review on this one is really just reviewing Newton's first law. An object at rest, correct answer here, will stay at rest. An object in motion will stay in motion, and unless acted upon by an unbalanced force. So we're going to focus on this unbalanced force thing, balanced or unbalanced, primarily in the study guide. Let's start with number one. The amount of force required to keep a 6 kilogram object moving with constant velocity of 2 meters per second is blank newtons. And the correct choice is F. Nonsense. A force is not required to keep an object in motion if, this is a big if it's moving at constant velocity. All right? An unbalanced force, that's where this comes in. So, is not needed. So something that is moving, let's take the easy example where there's no resistances. If we just took a ball in space and threw the ball, it would just keep going in a straight line, and after I release it, there's no other forces on it, and it would just keep moving and doing what it's doing. Now on Earth, there's a lot of unbalanced forces, so maybe we don't realize this, okay? When you throw a ball on Earth, it quickly goes down to the ground because gravity being an unbalanced force on it. When you slide something across the table, it comes to a stop because of friction being an unbalanced force on it. But if all the forces are either balanced or not present at all, things will just keep doing what they want to do, whether that be stay at rest or stay in motion at constant velocity. Another way to say this, and this comes to the next one, if there are unbalanced forces, you're going to have accelerations. You're either going to be speeding up, slowing down, or changing directions, because we learned in the past those are the 3 forms of acceleration. So for number 2, you just have to state whether it's balanced, whether there's an unbalanced force or not, from some old dot diagrams. If you follow the directions I told you, don't worry about writing a reason in. I will discuss them. The more important thing is right now is if you could simply identify if it's balanced or unbalanced. All right. So we could see in this picture from this dot diagram, this vehicle gets, the dots get further and further apart. Therefore, if you remember in the past, that means it is speeding up. That is a form of acceleration. And basically, like I said earlier, Newton's second law, one way to interpret it is you're only going to have acceleration if you have an unbalanced force. So yes, what would be the unbalanced force here? The force of your engine, your motor turning the wheels on your vehicle. Okay? And that provides you that acceleration. In the next one, we can see the dots stay spaced evenly apart. So, is there an unbalanced force? The answer is no. Spaced evenly means that it is moving at constant velocity. If you're moving at constant velocity, forces are either A, not there, or B, not present. Okay? So in a car on Earth, on a flat surface going at constant velocity, there's forces that are present on the horizontal axis, but they are in balance. So the forces would be some friction in one direction and your vehicle engine driving your wheels in the other direction, but just at the right amount that it keeps you going constant. Because if you're moving constant and you put in the gas and give yourself a bigger forward force from that, then you will unbalance those forces and you speed up. On the flip side, if you hit the brake, you will make friction the bigger unbalanced force, and actually the only unbalanced force in the other direction, and you would slow down. But the basic idea here is if there's acceleration, then yes, you have unbalanced forces. If you're at rest or at constant velocity, then no, there aren't no unbalanced forces. All right, in this one, we can see the dots get closer together. This car's slowing down. That's a form of acceleration. That must mean there's unbalanced forces on it. All right. One thing we've done, hopefully you've done up to this point, is a concept builder of recognizing forces and one on free body diagrams. Remember, free body diagrams are diagrams which have arrows to represent the forces acting on an object and what direction those forces are in. So number 3, it says each one of the dot diagrams in question number 2 could be matched to a force diagram below. The force diagrams depict the individual forces acting upon the car by a vector arrow. The arrow direction represents the direction of the force. The arrow length, this is important, represents the strength of the force. Match the dot diagrams from number 2 to a force diagram. Not every force diagram needs to be matched. All right, so for this force diagram, we have unbalanced forces on the x-axis. And actually, let me talk about something on the y-axis. For a car traveling on a flat road, flat straight road, the two forces on the y-axis are always going to be balanced because the car is not falling through the road and the road's not throwing the car up in the air. Okay, so really we're mostly concerned about these x-axis horizontal ones. So the first one best matches C. If I'm moving to the right, all these vehicles in A, B, and C are all moving to the right. If I'm moving to the right but slowing down, I have an imbalance to the left. All right, that would be like hitting your brakes in the car, because once you hit your brakes, you no longer have a forward force. You're not hitting the gas anymore, and friction is what slows you down. Pointing opposite, friction always opposes your motion, so that best matches with C. In this diagram, it shows an imbalanced force, a bigger one to the right. All right, that would best match speeding up. All right, you still have friction acting against your vehicle, but your engine is overcoming that friction enough to speed you up. So there's the unbalanced, and that would best match A. And this one best matches B because we have balanced forces. We do have forces this way and this way, but they're the same size in opposite directions, so they do balance, creating the possibility of a constant speed like in choice B. Number 4, if the net force acting upon an object is 0 newtons, net means total. That's from one of our vocab terms. Net force just means total force. And by the way, when we total up forces, we only do it on one axis at a time. So we never think of like totaling forces on this axis with forces on this one. All right. But with that being said, if the net force acting upon an object is 0 newtons, so that means balanced. The total is 0, say that's another way to say balance. Then the object must be either C or D, at rest or moving at constant speed, and that's really what Newton's law tells me. Okay, if it's unbalanced, we would be accelerating. Moving's too general of a term. Too many things could fall in there, so A's out. All right, moving along. Here's some old graphs that were given of some motion at various times during somebody's trip to school. Indicate whether Carson's vehicle is being acted on by an unbalanced force. Give a reason. The reason could be short and sweet here. All right. Remember, on a velocity time graph, this goes back a few weeks. If you take the slope of a velocity time graph, that gives me acceleration. And if you remember, the slope of a flat line is 0, so this one has 0 acceleration. This one has a negative slope because it's going downhill. This one has a positive slope, so this one has a negative acceleration. This one has a positive acceleration. Okay? Either way, what matters the most is you could have defined these ones include acceleration. A flat line on a VT graph, slope 0 means no acceleration. If there's no acceleration, then there's no unbalanced force, and the reason simply is because it has a slope of 0. In this one, yes, there's got to be unbalanced force. There's a non-zero acceleration is all you got to put for the reason. Same with this one. Unbalanced force, absolutely. That's not a flat line on a VT graph, so that is some non-zero acceleration. So yes, there has to be unbalanced forces. All right, now we're going to get to some free body diagrams with actual numbers in them. It says a free body diagram shows all the forces acting on an object. The net force is the vector sum of all these forces. Remember, on one axis at a time, though. Determine the net force and state if there's acceleration. All right, one thing that I'll give you guys I don't like about this, we should define what axis we're summing up the forces on, because notice, especially in A here, there's forces on this axis and this axis. So they weren't clear on that. There's only one choice on this one because there's only forces on one axis. But many times we do have forces on two axes. So the correct answer and the key is that the net force, and by the way, it tells us up here that sum or net force could be symbolized mathematically with this symbol. That's if you never saw this mathematical symbol in front of the F for force, it looks like almost like an E. It's a Greek letter called uppercase sigma, and in math it represents a total or a sum. Okay, so we should always state if the total is non-zero what direction it is in as well. So on the x-axis, there's an unbalanced force totaling, it is the only one, 10 newtons to the left. So since there's unbalanced force, there is acceleration on this axis. It didn't ask me for both axes, but it is balanced on this axis, 40 up, 40 down. All right. On these two, we have 20 up, 20 down. They balance, right? Balance is a simple idea. Therefore, the net total force represented by this symbolization here is 0 newtons. And if we have a net force on any axis of 0, there's no acceleration. So this whole thing just should all be coming together like one big important concept looked at in many different ways. Through graphs, through diagrams, through concepts, everything. This one, we have air resistance upward and gravitational force downward. They are different values. There is a difference of 40 or 15 newtons upward when we do the vector sum. And when we say vector sum, we total them but consider their direction when we total them. We don't add 40 to 25. That's not what the vector sum net force means. If one is up, we add it to negative 25, which is down, or in other words, subtract them. And the answer being the overall net force difference comes out to be in the direction of the bigger one, 15 newtons upward. Main point here is that there's non-zero net force, therefore there is acceleration. Number 7. During an in-class discussion, Analytical suggests to her lab partner that the dot diagram for the motion of an object in number 6b, that's this one, could be this. Okay, so 6b is here. Notice there's balanced forces on the y-axis and no forces on the x-axis. And his partner argues that the object in number 6b could not have any horizontal motion if there are only vertical forces acting on it. Who is right? Anna is correct. You could have motion with no forces. Let me go back to the example from earlier. All right. If I throw a ball in space and let it go, after I let it go, there's no more forces horizontally acting on it, but it would still keep going. All right. That's hard to see on Earth because there's so many resistance forces. But let's take real low resistance. Like let's take a hockey puck on ice. Yes, there is some friction, but it is very low. All right. If you slide a hockey puck on ice with any decent amount of force and let go, that puck is going to keep going probably till it hits the wall. Right. So if you ignore friction in that case because it's so low, the puck keeps moving even though there aren't any forces on there. So it is possible. Okay, so Anna's correct because it comes back to Newton's first law. If things are already in motion and there's no unbalanced forces acting on them, or in other words, another way to think about it is no forces at all acting on them, they'll just keep going and doing what they're doing. Number 8. During an in-class discussion, Aaron Agin asserts that the object in 6a must be moving to the left since the only horizontal force is acting to the left. Is he right? So in this one, the force to the left is friction. And he is not right. Friction opposes motion. This would be like taking any object, like your book, and sliding it to the right and letting it go. Once you let it go, there's no more forces to the right, but it's still moving to the right. And friction acts unbalanced to the left, which is actually what stops it. And finally, number 9. The diagrams below depict the magnitude and direction of the individual forces acting upon an object. Which objects could be moving to the right? Circle all that apply. All right, so this one A could be moving to the right. Why? Because we have balanced forces on the x-axis. So it could actually reasonably be moving either way. Okay? There's a possibility of it. As we just described in number 7, if there aren't any forces, it still could be moving on that x-axis. So B could be possible. C, we have a pull to the right or a push to the right, a force to the right. And it's unbalanced, so that could definitely mean it's moving to the right. It doesn't 100% mean it, but all this says what could be. Look in bold, it says could be. In D, this is like number 8. We could have an object sliding on a desk moving to the right with no more rightward force, but still moving against friction until it comes to a stop. And in a similar way, E could even be okay. E could still be moving to the right, so all these could be. I could be pulling on something to the right, but not hard enough to keep it moving, and maybe friction to the left eventually stops it and overcomes me. Okay? So all those are a possibility. I hope this helped, and remember, keep a hold of these, because any future tests or quizzes, which there may be a small one next week, you will be allowed to use this for. If there's any questions that maybe you have after watching this video the next time you are in class, or if you're a remote learner, if you're in class, say something. If you're a remote learner, email me or send me a class question through Google Classroom.